compound that I just recently discovered for myself called metformin. And metformin has been used previously as a treatment for type 2 diabetes, but in recent years it's been shown to have maybe some efficacy against some forms of cancer. So how cool would it be to have a already ready to go drug that we can just use as in a different way? And that's why we're going to be repurposing metformin in the struggle against cancer. So why don't we just start off actually on diabetes, since metformin was originally a diabetes therapy. But it makes sense that we should start there. Diabetes has two main forms: type 1, which is also known as juvenile diabetes, and this is caused by an inability of the body to produce its own insulin. It's usually caused by an autoimmune attack on the beta cells in the islet of Langerhans, which eventually shut down all insulin production, and you need to take insulin from outside of the body, artificially produced insulin. And then there is also type 2 diabetes, which is also known as adult onset diabetes, and it's caused by a overabundance, more or less, of insulin in your system. If you have too much insulin coursing through your body over too long a time, you'll build up a resistance to it, and it will decrease your sensitivity to insulin, which decreases your ability to take out glucose to get energy, more or less. And so, like I said, metformin is still a therapy for type 2 diabetes, and it's actually the most prescribed diabetes medication in the world, aside from insulin, of course. Also, a bonus fact, while you're on metformin, you have a decreased risk of cardiovascular-related death. So, killing two birds with one stone with that one. But unfortunately, the mechanism of action for metformin is poorly understood. What we do know, however, is that it decreases the process of gluconeogenesis, which is different from glycogenolysis, which is the breaking down of a starch-like molecule in the liver, and it is instead a recombining of two metabolic products into a new sugar molecule. So metformin shuts that down in the liver. It also increases your insulin sensitivity, which is also interesting because a lot of cancers are very already insulin sensitive. So we'll get into that a little bit later. And it also enhances the glucose uptake of your extremities. Your peripheral glucose uptake is enhanced with metformin. So a little bit about the history of metformin. In the days way back, in ancient Roman times, back in ancient East Asia, French lilac was used to treat the symptoms of diabetes, and metformin is actually derived from French lilac extract. So they were a bit smarter than we give them credit for. But it wasn't until 1922 when metformin was actually first synthesized and described as a byproduct of N,N-dimethylguanidine, which you can see right here. And you can actually see how similar these two molecules actually are. You can definitely see how you can get one from the other. And also in 1922, insulin was first used as a treatment for type 2 diabetes. But getting back to metformin, its blood sugar lowering qualities were first found out in 1929. However, shortly after that, the interest in metformin and other biguanides decreased as a result of increasing interest in insulin as the first-line treatment for diabetes. So it takes another about 30 years until metformin comes into the spotlight again, and it's then that metformin is used in the treatment of diabetes. But it still didn't take hold until 1979, almost 20 years after that it was first marketed in France as glucophage, glucose eater. But still, it hasn't really gotten a hold until 1994 when the US FDA gave its approval for the market of metformin in America. So you can just see this almost over 70 year in fact, line where metformin, we knew about it, we knew what it could do, but we just didn't pay much attention to it, which is unfortunate because who knows, we could have been going through this presentation 20 some odd years ago if we go by the timeline of this. Anyways, now that we've gotten diabetes out of the way, let me give you a little bit of information on cancer. And what cancer basically is a unregulated division of cells caused normally by a mutation in a oncogene, and these genes just turn on the cell replication cycle without mediation. It just your cells just keep dividing and it just won't stop. And also tumor cells can alter the cellular functions, normal cellular functions of the cell. Namely, they will downregulate oxidative phosphorylation, which is basically the main way that your normal cells get oxygen, get ATP out of the things that you eat. So like I said, cancer metabolism is different than normal cells. Cancer cells require more oxygen because, like I say, they're dividing so fast. They need more energy to sustain this replication. And it was hypothesized by Otto Warburg in Germany in the early 20th century that cancer cells actually cause a upregulation of an anaerobic metabolic pathway called glycolysis. And this effect, this shift from oxidative phosphorylation to glycolysis is called the Warburg effect after the eminent scientist who first observed it. And also, like I was mentioning before, insulin is not only important in the uptaking of glucose from the blood, but it is also a very strong enhancer of proliferation. So if you have a lot of insulin in a cancer cell, not only will it take off glucose, but it will also spread that much faster. So, getting back to metformin, these are some of what they think are some of the possible modes of action that metformin can take against cancer cells. But this seems like a lot, so we'll only focus on this bit over here. But let's talk about this line here, starting first with Mtor. Like, what is Mtor? Mtor is a mammalian target of rapamycin. There are a lot of targets of rapamycin in the animal kingdom, but as mammals, we inherit the mammalian version of it. And what Mtor does is it regulates energy production and consumption. If you activate the Mtor protein, it will continue to use energy. It will continue to use ATP in a wide variety of activities. And also, if you inhibit Mtor, it will slow down the energy consumption of the cell, allowing it to recuperate from the sustained energy utilization of the activation of Mtor. Now, if you if you activate mTOR for too long of a time, you start to lose energy very, very fast. And eventually you'll end up with an overabundance of a compound called AMP, which is adenosine monophosphate, which if it gets to too high of a number, will activate AMPK, adenosine monophosphate activated protein kinase. And when AMPK is activated, it will inhibit mTOR, shut it off, and allow the cell to regenerate its supply of energy. Sorry. And also it will upregulate downstream autophagy. But let's think about that word autophagy. Just let's break it down for a second. Autophagy, self-eating. That's quite strange when you think about it, but what it really is just a cleaning up of the cell. It will, when you upregulate autophagy, the cell will break down any unused or redundant proteins and then recycle those amino acids from the degradation to make new amino acids, or new proteins, rather, I apologize. And fun fact, if you upregulate autophagy, it's implied that you will also live longer, so that's just a little fun fact. I found it interesting. Anyways, so let's just all think through the big picture of this pathway, if you will. Here we have mTOR and then AMPK, and at the very end of it all, autophagy. So now if we introduce metformin, if you'll remember, this is metformin. If we introduce metformin into the system, it will cause a increase in the amount of AMP, which we don't, and at this point we don't know how, but I'll get into that later. I'll explain to you later. And this increase in the amount of AMP will activate AMPK, which down the line will inhibit mTOR. But if we introduce insulin into the system as well, it will instead activate mTOR, and whichever you have more of, more activation of AMPK or more insulin in the system, that one will win. But let's pretend that we have more AMPK and are now inhibiting mTOR. The inhibition of mTOR will upregulate autophagy, which will degrade any malignant proteins within the cell, and thereby preventing cancer in any normal tissues that are not already cancerous, and also breaking down and the infrastructure of the cancer cells themselves. But unfortunately, it's not as simple as that. mTOR, if activated, like I said, uses energy, and some of this energy goes to proliferation, to cell division. And if the tumor grows too fast, then insufficient levels of oxygen will accumulate in the cell. And this will, in turn, activate hypoxia-inducible factor. I apologize for my stutter. Or HIF. And upregulation of HIF will in turn cause an upregulation of hypoxia-specific genes, some of which are involved in glycolysis, glycolytic enzymes, or VEGF, vascular endothelial growth factor, bringing more blood into the cell, and other hypoxia-specific genes. And this really just causes a self-perpetuating cycle. The loss of oxygen in the cell just increases the expression of HIF, which then increases the dependence on anaerobic energy production, glycolysis. And this increasing glycolysis in turn affects that and this. So it's just horrible, horrible cycle that just needs to be broken. But how can metformin do this? How can it break this self-perpetuating cycle? Well, it turns out that Will Wheaton, not that Will Wheaton, but the other Will Wheaton, and his colleagues did a study about this, and they found, and the study is titled "Metformin Inhibits Mitochondrial Complex 1 of Cancer Cells to Reduce Tumorigenesis." So let's break that down. Metformin turns off the mitochondrial complex 1, shuts down the production of energy in the mitochondria, the powerhouse of the cell, to reduce tumorigenesis, to stop the tumor cells from dividing, stop the tumor from growing. So what did they actually do in this study? Well, they took some prostate cancer cells, the HCC116 line, and they mutated some of those to express this protein, NDI1, which which forces, more or less, oxidative phosphorylation. No matter what, NDI1-induced HCT116 cells should always use oxidative phosphorylation in their energy production, regardless of any other conditions. So this will be our positive control to see whether metformin actually works on these cancer cells. So first, let's look at some of their results. This on the survivability, the viability, and proliferation of cancer cells. So as you can see up here we have the normal cells and our positive control over here. Now, these tests up here are being fed glucose as well as metformin. And as you can see, there's not really a whole lot that's going on. We're feeding them glucose, so there's really nothing more that they can do. They're probably having a party in their little well plates. But if we take away glucose and instead feed them a combination of lactate and, citrate and malate in the glucose-free media, along with metformin, we see that as we increase the concentration of metformin, the viability, the ability of the cells to survive and propagate goes down. So that makes sense, right? If we're not giving them free food, free energy, then we should be affecting them. And as you can see over here at the positive controls, again, nothing is happening because it always uses oxidative phosphorylation. So really, the next question here is, why is this happening? What exactly is causing this? So they looked at the energy consumption in the cells, and again, you see our positive control in our normal cells, and they looked at the percent of oxygen consumption with regards to normal cells. And as we can see, if we increase the concentration of metformin, the ability of the cells to produce energy, to consume oxygen, goes down. And again, nothing is happening in the positive control as should be happening. But what's interesting here is that up here, these cells are intact, or their cell membranes have not been tampered with. But down here, their cell membranes have been permeabilized, making it easier for substances to come in and out of the cell. So if we look at what they did with metformin compared to up here, it looks like metformin is affecting the cells more if it's easier to get into the cell. Now, that makes sense. If it's easier to get more into the cell, then we should see a greater effect by the metformin. And then this is another oxygen consumption assay. This time looking more at time-dependent controls rather than concentration. And what's interesting about this series of tests here is that instead of they focus on the timing of inducing oxygen consumption, energy production, and the introduction of metformin in the cell. ADP is just another version of ATP, a less energetic version, but one that is more easily energized, made energetic in the mitochondria. And CCCP, it's a Russian joke. CCCP will induce energy consumption, or oxygen consumption, I apologize, and energy production, but it will also depolarize the cell, the membrane of the mitochondria. And this is significant because in the mitochondria you need to have a electrochemical gradient by pumping out protons and letting them flow back in through the ATP synthase, which creates ATP. And antimycin is used here to shut down the electron transport chain, the production of ATP in the cell. So as you can see, if we introduce metformin with just ADP, the ability of the cell to produce energy goes down, and that's what we want. However, down here they use rotenone, which is another inhibitor of energy production, but instead this is a irreversible bind. Rotenone irreversibly binds complex 1 of the mitochondria in the electron transport chain. So this should shut down energy production, which it does in both cases. However, metformin does not shut down energy production here, which would suggest that metformin's action is predicated on the existence of a stable membrane potential in the mitochondria. And if we look at their next assay, we see that they just changed the timing of the metformin as opposed to oxygen consumption inducer. And we can see that when metformin is introduced first and then CCCP, it goes back to normal. And this would indicate, again, that metformin requires a stable membrane potential to do its thing. Okay, so here, now that we've talked about energy consumption in the cell, that would lead straight into HIF, hypoxia-inducible factor. And this up here are some Western blots that we can use to show the expression of certain proteins, and this down here is just a quantitative, version of these Western blots. Now, let me just walk you through each of these conditions here. These two are normoxic, under 21% oxygen, whereas these two are hypoxic, under only 1.5% oxygen. And these two have been treated with DFO, which is an iron chelator, which stabilizes the HIF1 alpha protein. So anything that's there just stays there and will not be degraded. And so, if we see here, these two have been treated with metformin. The normoxic has no expression because it isn't in hypoxia. It doesn't have hypoxia-inducible factor. Whereas this one, however, under hypoxic conditions, has quite a bit less expression of HIF in the cells. As you can see in the mutant cells, there is no significant difference. It's more or less the same, which is as it should be. And further, we know that HIF is being decreased in these cells as opposed to without treatment with metformin, because we can detect its target genes, HIF's target genes. So these conditions are under normoxia, which you can see that there is no big expression of VEGF or growth factor, vascular endothelial growth factor. Whereas with these under hypoxic conditions being treated with increasing amounts of metformin, do show a decreased expression of these genes, or more specifically their mRNAs, their transcripts to be produced and to be translated into proteins. And again, the positive control, it's no change, and again over here no change. And CA9 is just another growth factor. It's another inducer of proliferation. And again, with increasing amounts of metformin, we can decrease the expression of these mRNAs. So wonderful. Let's start to wrap it up here. What conclusions can be made from this study? Metformin reversibly interferes with the mitochondrial complex 1, but only with a intact membrane potential, untampered with and normal membrane potential. And under unfavorable nutrient conditions, if it's starved of glucose, metformin decreases the cell viability and the ability of the tumor cells to grow and proliferate. And lastly, metformin decreases the expression of HIF1 alpha specifically, and its downstream target genes under hypoxic conditions, which again, like I was saying, stop that HIF cycle and kill the cell, hopefully. So, if we're going to tie it all together, we have metformin, who inhibits the complex 1 in the mitochondria, which decreases oxygen consumption and simultaneously, hand in hand, decreases ATP production, which is energetically unfavorable, if you remember, which upregulates AMP and downstream inhibits Mtor and activates protein synthesis or autophagy, breaking down of proteins and making new ones. And this consumption of oxygen increases the this downregulation, of oxygen consumption, increases the amount of oxygen within the cell, thus negating hypoxia, turning it back to normoxic conditions, and downregulating HIF along with any other downstream genes that HIF happens to target. Now, in the future, hopefully we'll be able to see metformin in a cocktail of other cancer therapies, including PI3 kinases, which inhibit the uptake of glucose, which, as we were discussing before, strangles the tumor cells of glucose, making the cell energetically unfavorable, and then activating AMPK down the line, and also angiogenesis inhibitors, which prevent blood vessels from being formed to the cells, which strangle it of both glucose and oxygen, which I'm sure you can imagine what being strangled of oxygen would be. Wouldn't be able to produce HIF and downstream genes and glucose discussed. So, I'll take some time to thank you all, but in particular Dr. Dave Hall for being a wonderful mentor throughout this entire process of making this talk. Professors Deanna Donahue and Allison Fleshman for sticking with us and listening to our horrible practice runs, I'm sure. Dr. Stephan Debert for being a wonderful advisor for the short amount of time that we were advisor-advisee, but still nonetheless a very profound influence on my future career. And my parents, Trevor and Tammy LaRene, who unfortunately couldn't be here today, but for always supporting me in all of my doings here and home. So, splashing my references, let you know I'm not stealing anything, and I'll entertain any questions now.
Talk a little more about the interplay between autophagy and cancer. It would seem like if we're going to fight cancer, should we try to regulate autophagy or down-regulate it?
That's the idea. If we want to live longer, healthier, we should be focusing more on upregulating autophagy because it breaks down any unnecessary proteins, any misfolded proteins as well, and just makes the whole cell environment cleaner and more nice to live in.
What might be a downside?
A downside of autophagy?
Upregulating autophagy in cancer.
In cancer, that's actually
What is cancer, right? Cancer is cells that won't die.
Right, yeah.
Autophagy would seem to help them not die.
That is a very good point, yes. However, in the cancer cells, because they're replicating so fast, because they're doing all of these very energetic things so fast, there can be a lot of mistakes made in the production of proteins, and these mistakes in the protein process can make cancer cells more malignant, more likely to spread or metastasize even. And so if we break down these proteins, then hopefully we can reduce the likelihood of that happening.
So I know from personal experience that cancer drugs can be really, really nasty. So what kind of nasty side effects does metformin come?
In the past, and when they were exclusively using it as a diabetes drug, it came with some nausea, some lightheadedness. So not a lot, but I mean, just anything you could think of for a regular chemotherapy drug. I'm sure metformin would exhibit it, but in less so.
Do the people that used to treat it for diabetes show the same symptoms?
Metformin hasn't been used as a full cancer therapy yet, but if you can imagine taking it for cancer rather than diabetes, I'm sure the side effects would be more or less the same. And from what I could tell, the side effects of metformin are similar to other chemotherapy drugs, but in a more calmed down way, less intense than other chemotherapy drugs. So
Is this the direction? I understand that they're developing some cancer therapies that don't have some of the side effects of the chemotherapy or the radiation because they attack the cancer cells directly. I think this is what you're getting to.
yes. This metformin, while it does affect other cells in the body, and that's where you get the side effects from, metformin can be targeted very more or less precisely because because of the increase in the hypoxic conditions of tumor cells. So it will flow naturally to there.
Any questions? Oh, there we go.
You said the inhibition of Mtor is causing an increase in the autophagy.
Yes.
So, what are some side effects or, I guess, different results if Mtor is instead promoted within the body?
If Mtor is promoted in the body, that's where you get the proliferation, the out of control division of the cells, because it's like I said, activation of Mtor promotes the use of energy, and cell division is a very energetic process that takes place within the cell. And so if we activate, upregulate Mtor, then we are giving our cells free rein to divide willy-nilly, which is kind of the opposite of what we want in cancer.
So, so just to get some clarification, so metformin reduces the consumption or the ability for consumption of oxygen, or backwards of that?
No, yeah, it reduces the cell's ability to consume oxygen, and thereby reduces the ability to produce ATP, to produce energy.
So are there other, so this drug was discovered or used some centuries ago. Are there other drugs, especially those from more like natural products like the French salad you mentioned, are there other drugs that now that they've identified that this is a good thing to stop the H1F cycle, are there other drugs that they can go back to that show those similar conditions that then they can maybe apply as alternative cancer treatments like metformin?
There's another compound in the same family as metformin called fenformin, which was a diabetes drug, and they even used it in this study as just a kind of control to see whether metformin and fenformin do the same thing, and it turns out that they do to cancer cells. But fenformin is a lot more adverse to take. It has a lot harsher side effects than metformin, so that's why they decided to go with metformin rather than others like
If I understand correctly, there are a lot of different forms of cancer.
True, yeah.
And one medication may work on one, but not on another.
Yeah, that's very, very true, yes. Some cancers are induced by certain genes and will therefore make it resistant to some forms of therapy, while others are, free to be attacked by anything less malignant. But yeah, that's absolutely correct. Yeah. Yes.
Now, would you say metformin would be something to inhibit cancer?
I would say that yes, metformin is a inhibitor of cancer even starting. Yeah, I think even in addition to the cardiovascular related death the decrease in that risk, I think they also I read somewhere that you also have a decreased risk of developing certain types of cancer while on metformin, such as breast cancer, prostate cancer, and others as well. I can't remember exactly.
Let's thank our speaker again.